So welcome everyone to RISE Learning Machine Seminars. My name is Alexis and I work here at RISE as a machine learning researcher focusing on climate and environmental applications. RISE is Sweden's public research institute, and this is our weekly seminar on AI and machine learning. This particular session is hosted jointly with Climate AI Nordics, a new research network in the Nordics that gathers researchers focusing on the intersection between AI, climate, and environment. The meeting will be recorded, and please let us know if you would like to be removed. And make sure that you check out our great collection of talks on YouTube as well. And today I have the great pleasure of introducing Hakim Abdi at Lund University. You're a senior lecturer at the Center for Environmental and Climate Science. Hakim is a geographer and environmental scientist who specializes in the interaction between natural ecosystems and human activity. Your research focuses on leveraging remote sensing, machine learning, and spatial analysis to improve biodiversity monitoring and conservation efforts. And his current work is on mapping tree species composition using satellite imagery to enhance forest management strategies. And today's topic that you will be talking about is tech-informed nature conservation. Are we there yet? Welcome.
Thank you very much, Alexis, and hello, everybody. And I'm a senior researcher, not senior lecturer, not yet at least.
Sorry, yes.
So, welcome everybody to this talk. I'm going to share my screen. Yeah, can everybody see my screen? Just give me a thumbs up if you do, please.
Looks very good.
Yeah, all right, thank you. Right. So I'm going to get right into it. So the overview of this is the overview of today's talk. I'm going to get into a little bit of a background about remote sensing technology and why it's really an important component in today's nature conservation strategies. Then I'm going to get into some opportunities and challenges with using this data and some case studies. And then finally, we're going to wrap up and we're going to try and answer the question of whether we're there yet. And I also want to mention that AI is a part of this process. It's not a central part. I'm not an AI expert, but I'm an AI user. But we'll also talk about the utility of this technology in combination with remote sensing. So remote sensing comes in different flavors, depending on which system that you would like to look at, which system you would like to protect, which system you would like to study. The sensing capabilities of remote sensing sensors range from drones and tower-based sensors all the way to satellites, as you're probably aware. And the real power here lies in our ability to choose which sensor combinations to combine. So, for example, if we are interested in conserving butterflies, a certain species of butterfly, we probably don't need a large-scale satellite image for that. A drone data or airborne data may suffice. But if we're trying to conserve the habitat of the wolf that spans a very large spatial range, then we might go for satellite-based sensors. But the ability that we are able to combine drone-based imagery, airborne imagery with satellite data, this multi-scalar process is really where the power of remote sensing lies. I mean, the power of the data that we have available today. That's where most of the advantages come from. Because when we look at certain processes, certain physical and biological processes that happen at a much smaller scale, we won't be able to observe them using satellites. So when we combine high-level high-scale, centimeter-scale observations from drones or from ground sensors, and then we upscale them with satellites, we're able to transform that detailed information across a much larger area. And this is really what we are able to do today that we couldn't do 10 or even 20 years ago. And another aspect is the combination of both the spatial, the multiscalar that I just mentioned, and the temporal information. Because these systems look at the Earth, they look at the landscape at regular intervals. Whether you're using a satellite or you're using airborne sensors that go once a year or twice a year, or even drones that you use at certain intervals during the season along some predefined routes. So regardless, we're able to look at systems temporally as well as spatially. And this is important for the very simple fact that we understand how ecosystems change in relation to external factors based on their temporal signatures. So, for example, we have areas of forests where we can monitor the health of the forest. So, for example, if you look at the curve above, this is something called the vegetation index, which I'll get to shortly. But in summary, it gives us an indication of the health of an ecosystem. So if we look at this vegetation index over time, we see that it is a fairly healthy forest. But all of a sudden, we notice there's a drop in the signal, right? And we're able to then study why this drop happened because of the forest being completely gone. And then we're able to study the recovery of the forest after that major disturbance. So from this simple example, you can see the power of the temporal signature when you combine it with the spatial data. And then you're able to take that and expand it across large continents with satellite information. And you're able to figure out when the disturbance happened, how severe the disturbance was. And for the purposes of nature conservation, this is really important information. If we want to figure out whether our conservation strategies are being effective, we want to know exactly how healthy a system is. And the key aspect of these sensors is that they represent actual biophysics that are happening in the vegetative canopy. So plants absorb very strongly in the red and the blue parts of the electromagnetic spectrum. They reflect a little bit in the green, which is why we see them as green. But they reflect even more in, I don't know if I can get out of the camera, but they reflect even more in the near infrared. But we cannot see the infrared signatures. Otherwise, all the planets would have been really bright according to our eyes. But the satellite sensors can. And we use this information, the satellite sensors can. We design the satellite sensors for them to sense the near infrared. And we can use this information in order to study how ecosystems are doing. So if we take this information and we spatialize it, we turn it into actual maps. We're able to look at spatial variations in ecosystem health. So I'm sure some of you have heard of something called NDVI, which is the greenness index. It is something that is being used a lot these days to look at health of vegetation, and it's based on this very, very simple concept of the strong reflectance in the near infrared. So if you pay attention to that curve on the left side of the image, if you see that the reflectance of this particular plant is 48% in the near infrared, the absorption in the red is about 6. When you take the difference of those two and you divide them by their sum, you get a number between 0 and 1, which is an indicator of how healthy that plant is. So the closer the number it is to 1, the healthier the plant. The closer it is to 0, the plant's not doing so well. So it's a simple to understand metric. There are tons of these different vegetation indices that are designed for different applications. Some look at algal blooms, some look at crop yield, others look at forest health. So they can be designed for a variety of applications. And they, as you can see from the image on the right side, they can really capture the variability in the health of vegetation in the ecosystem. And this is an area in Lund, by the way. That's Krankeken on the left, that lake, and on the right is Vom. And it's an area of mixed-use pastures and forests. And we're able to link observations with ecosystem health in a quantitative way, which helps us infer information about the environment. When we take this information temporally, then we can see how different land uses are changing. If we're looking at an agricultural landscape, for example, there are a lot of birds, for example, these days that are declining in number because of intensive agriculture. So we're able to study these systems and see how they're intensively being managed, compare them to natural systems using their temporal signature, and create maps like this that show us when the season started, the growing season, when it ends, and what the maximum productivity is of these areas, to compare whether we should be talking to farmers of how to better manage their land to make it even less intensive for biodiversity. And where machine learning and AI comes in is really to infer information from these data, to optimize how this data is being produced, to predict, to make predictions in areas where we don't have information, and to forecast this information into the future. And this is really where the power is. I'm using AI here in a very big catch-all net that includes all these predictive techniques. So we use AI as remote sensing scientists and geographers to basically convert observations of habitats as observed by the satellite to information about habitats. And then when we have this information on regular intervals, year after year, we're able to study how the landscape is changing. If we see, for example, that some high value or high nature value habitats are decreasing, then we can make interventions to remedy that. And without this information, it's very difficult for us to actually keep collecting the field data without getting that big picture of what is really happening across the landscape. And this is really where the power lies. So habitats are critical. I mean, you're hearing me say habitats and ecosystems a lot because it's really at the crux of remote sensing science, because we cannot observe the organisms themselves. And we cannot see the birds, we can't see the insects, but we know where they live, and we know what they prefer. We know their ecology, we know their biology. So we're able then to link those two together. And habitat heterogeneity is really a key part here, because the more diverse the habitat is, the more species that you have. That's a key part of ecosystem ecology. And the techniques that we use is that, we have information of where the species lives and what it prefers, and we make a link of that information with information about their habitats, right? So you have species that prefer a certain kind of tree or a certain kind of collection of trees, right? Maybe there are the species that like to live in agricultural areas that are less intensively managed. And there are plenty of those right now, which is why they're decreasing in number. So we're able to take this information and combine it with remote sensing data in order to map their habitats. This is a good example. So this bird is called the white-backed woodpecker. It's critically endangered in Sweden. Its numbers are decreasing quickly because it prefers old deciduous forests, which are very low in number in Sweden because they're being replaced with spruce-dominated production forests. So since we know what this species prefers, we're able to map its habitats, right? Aggregate the numbers, and then provide information to stakeholders of where this species could potentially occur, and maybe protect or survey of those areas. So we're optimizing. This is optimization I was talking about. Instead, because in a big country like Sweden, you can't go everywhere, right? You have to figure out a way to optimize the field data collection and the protection strategies. And national monitoring programs are really a cornerstone of this. They already provide data for ecologists and for scientists to use. But unfortunately, they are, as I was discussing with some of you today, they are limited in their extent due to lack of human or financial resources. But there is, as you can see from this table, there's a wealth of different remote sensing products that can be used for different things that can be linked with this national monitoring program. And there is, the potential today is really huge when it comes to linking these two, and it's something that I've observed is not being used to its full potential. And I have it on good authority that the institutions that collect this want people to use this hard-earned field data into something that is very that can be optimized. Let's put it that way, using predictive methods. And we're very lucky here in Sweden to have a wealth of environmental monitoring programs that look at different things. From natural landscapes to butterflies, to birds. So if we combine this information with this new product that's been launched over the last 10 years, the Copernicus program from the European Commission, with its wide variety of different satellite systems looking at different things, we're able to really provide products that use the monitoring data to inform conservation. On top of that, we have drones on the market now that are easily accessible more than they were like 5 years ago. Like we have multispectral drones now that are affordable, that can be purchased for reasonable price and deployed at different markets. And on top of that, we have a wealth of predictive tools and open source tools. I mean, anybody can learn these tools these days because a lot of them are open, and there are so many courses and Coursera and so on. So all the pieces are in place. We just need to kind of put them all together, and that's the message I'm trying to give. So now I'm gonna put my money where my mouth is, and I'm gonna show you what we are doing with this data. So we took data from the Swedish National Forest Inventory, and what we are doing is we are looking at the distribution of different tree species in Sweden. So these are what the plots look like, they're distributed across the country. And when you look at individual forests, they look like this. You can't tell what's what. It's very difficult. You don't know what's a high-value forest, what's a low-value forest, what species there are. So we're using satellite data to try and tease out the signals of these different species and put them in a machine learning framework. And we are then mapping those different tree species across landscapes. And then this information can be further refined into information about the biodiversity value by relevant authorities who are trying to protect habitats. The other thing is that currently there are a plethora of different studies that look at different systems using the combination of remote sensing and machine learning. You have studies that look at forest ecosystems. We talked a little bit about that. There are studies that look at agricultural systems. Studies that extract habitat metrics, specific metrics for certain conservation objectives, grasslands and pastures, and even studies that are trying to innovate by counting individual birds. In this case, these are the cranes, the trana, like those big birds. They are counting them using airborne imagery over their roosting sites. So there's a lot of opportunities to capture the signal and use it for management. Regarding specific case studies, so there's a very cool study that, out of Finland, and this study. So they were trying to protect this bird called the northern lapwing, tofsvipa in Swedish, and it's an agricultural species. It nests in low-intensity agricultural land, but as I mentioned, this habitat is decreasing very quickly in Europe. So what they did is that they, in order to conserve the species, they use a drone that is equipped with a thermal sensor. And they flew the drone along predefined paths to detect where the nests are in the agricultural landscape, because the nests are warmer than the surrounding agriculture. And once the nests are located, then that location is relayed to the machine that is the plowing or harvesting the field. And when the machine knows where the nest is, the machinery is raised so as not to destroy the nest. And then when it passes the nest, the machinery goes back down. I mean, this is really cool, because this is a really cool use of machine learning, remote sensing, and technology in order to conserve a species. But because usually the way this is done is you go manually. You go to the field with a telescope. You're trying to figure out where the nests are and then locate the nests.
Could one imagine having the camera on this tractor instead? I'm just wondering, like, they use a drone to map them, but then there's a tractor or something.
Yes. So I don't know how big the how accessible the tractor is, because like you need to have a good view of the nest. Sure. In order to map it. So
true.
Yeah. But it was a very cool activity nonetheless, and I hope it's being deployed in a more operational way, because it saves a lot of time. And the other example is from Brazil, where they use environmental DNA along with remote sensing, and they combine these two using some predictive algorithm. And what they're trying to do here is that they're trying to convince people with livestock in Brazil, because as you know, livestock is the main cause of deforestation in Brazil. So what they're trying to do is convince them to go to, instead towards shaded coca, because the economy is apparently very similar. So what they want people to do is go to shaded coca, because shaded coca plantations have similar biodiversity benefits as secondary forests. So what they did is that they took environmental DNA across some sites, and they linked that with remote sensing data to expand over a large area. And what they found is that the community composition of certain species is similar in shaded coca plantations as they are in secondary forests, which are forests that have been allowed to regrow after deforestation. So with the combination of eDNA, machine learning, and remote sensing, what they did is that they were able to provide information to stakeholders about what kind of conservation-focused land use to apply. And I think this is also a very, very innovative application of all these factors. The third one is from Chile and New Zealand, and here what they used is they used drone data to provide to be a substitute for field samples. So, for example, what they did is they used drone data to look at individual plant species and vegetation types. So usually the way this is done is in the field is using what's called a transect system, where you have a tape measure and you go along the tape measure and you measure and you kind of identify which species there are and how many there are. What they're doing here, they're optimizing this by using drones. And with the drones, they've upscaled those predictions to the sentinel level in a way as a way to either eliminate or complement the field measurement. And they found a fairly good accuracy of roughly 80% explained variance. And I found this one to be particularly interesting because it really takes the rigors of field work out of the equation. So you can use drones along predefined routes instead of walking 500, 700 kilometers in order to collect the data. 500, 700 meters in order to collect the data. And that's very an efficient efficient use of field data. The fourth study is the one that I was personally involved in, and this study involves the surveying of important bird and biodiversity areas to really figure out how the rapid changes in the landscape are affecting the diversity and abundance of wintering birds. Because Tunisia lies in this very unique area where the birds that come from Northern Europe use the country as a stopover before they cross the Sahara. So if the birds are not well equipped nutritionally, then they will die in the desert, right? So what we try to do is look at what are the characteristics of the landscape and use that information to inform management. And we found that landscape composition, configuration, and function significantly affected both the diversity and abundance of water birds. And we formulated recommendations for the municipalities of how to best manage the area where these water birds are using. I'm particularly proud of this study because we are able to draft a document that could be used for policy making. The final example is from a relatively new phenomenon, at least when it comes to policies. So there's a new EU nature restoration law that's out, and rewilding of abandoned or degraded areas is an important part of it. And remote sensing is still not at the forefront of this research area, but there are studies, for example, this study from 2022 that are exploring the possibilities of using remote sensing to look at the before and the after of rewilding to see how effective it has become. And with rewilding, there's this passive rewilding where you just let the land, you let nature take over. And there's active rewilding where you introduce species. And for both types, the distribution of the habitats and the complexity of the habitats changes, which is something that you can see in the before and after of sites, and then you can actually even assess what the relative changes are. And you can combine this information with information of other remote sensing techniques like camera traps or in situ sensors to link to this information. And it's really a cost-effective method to assess if the rewilding is working or not. So now we go to the challenges. And with nature conservation, with ecology, a key part here is the why is very important. Why something is happening is really a critical part of this. And which is why a lot of studies have used simple explainable methods to explain the phenomena. But these days we have very complicated and very, very accurate methods to describe systems. And the problem with these is that they're very difficult to explain. It's very difficult to explain to stakeholders, why why the model shows what it shows. Whereas for simple statistical methods, it's relatively easy to explain to a person how it works. But that's changing. There's a lot of techniques coming out to try and explain and open up these boxes. I don't know how effective they are, quite frankly. but there is an active effort to unbox the high-level machine learning methods. And actually, interpretability, simplicity, and transparency are really also key reasons, by the way, that big financial institutions still use things like logistic regression and linear regression in order to decide which lenders to take because they're easier to explain to their. So yeah, explainability is a big thing. The other thing is accuracy versus representativeness and generalizability. Um, a lot of these models are super accurate, 95, 98, 99% accuracy, which is like really mind-boggling. So I'm going to give you a quick example of why some of these models may not be representative. So if we look at the border area between these three countries, and I have a stakeholder that wants to map spruce and birch, right? So I go to the Polish side and I do the mapping because it's easier. There's more roads in the Polish side. It's easier. Let's say hypothetically, right? So I do my mapping there. I make a nice model. I do my cross validation. I get very nice accuracy. Boom. It's good, right? I've done my map. That's it. But really, is this model representative across the whole landscape? That's the question, right? Is the model that I created here in Poland, where there is different kind of land use. As you can see, there's less clear cuts in Poland than there are in Lithuania, and almost no clear cuts in Belarus. How does that affect the reflectance that's received by the satellite signal, right? There's a lot of variables at play here. We don't know, right? So ideally, this creates a data leakage problem where things that models that are trained on certain subsets are generalized across larger subsets. And that's people are quickly realizing that this is a problem. Ideally, for this particular example, the sampling should have been more like this. We're looking at this tri-state area. So that's one thing. Data leakage is and representativeness is one thing. The other thing is interdisciplinary miscommunication. Because there are a lot of stakeholders in nature conservation. There are geographers, there are ecologists, there are data scientists, there are landowners. There's a lot of room for miscommunication. That's happened quite often, actually. It happens quite often. And there needs to be really a lot of active exchange of information between different groups in languages that the different groups understand. Because sometimes data leakage is a good example, right? If that information is not communicated clearly that this is a potential issue, it might not be considered, and the models that on which the decisions are made may not be. And the technology introduction, because technology is moving at a much faster pace than society, so there needs to be proper knowledge transfer through comprehensive planning with everybody involved there from the start to the finish. So it has to be ideally a continuous process from the planning phase to the reporting phase. And unfortunately, that doesn't happen often for the sake of expedience. So the conclusions are, so that there's a strong potential to combine all these different technologies. Accessibility for field data needs to be improved through things like APIs for quick access of information from the agencies that collect this information. The satellite data is already easily accessible through these API systems, so the national or regional agencies need to catch up to that and make their data easily accessible. There needs to be some adaptive protocols that can improve the predictions, for example, by taking into consideration this data leakage problem that we talked about. And there needs to be safeguards to really make sure that the maps and the data that's being produced to the stakeholders are actually correct. And continuous communication, of course, is essential for this. So, are we there yet? I would say we're getting there. I mean, all this technology is happening within the last 10 years. So it's not a long time for people to adapt to the process, but we have everything ready. The technology is there, the expertise are there, the data is there, and what's needed is domain-specific integration with all these experts that are involved to talk to each other, and the involvement of other stakeholders like landowners and policymakers as well. And once this is streamlined, I feel that things will kind of fall into place. But at this point in time, the reason I put we're getting there is that things seem to be in individual bubbles that don't necessarily communicate with each other. Yeah, that's it. Thank you very much.
Thank you very much, Hakim, for this great talk today, and very good thoughts. I think there's a lot of people in the room and in Zoom that recognize some of these challenges that you lay out today. So yeah, with this, I'd just like to open the floor for questions and discussion, both here in Lund and also at Zoom. So just shout out.
I have a couple of questions.
Yeah,
please go.
So you were mentioning the generalizability issues, and with a particular example of the tree mapping in Poland. What are the sort of the solutions here, and what are the would you say the typical like how bad is it? The models that we use today, if you use the model trained in Poland, is it worthless in Belarus, for example?
Yeah, I mean, I wouldn't say it's worthless. I would say maybe it's not entirely accurate, because when you look at the remote sensing signal, there's considerable variations. So let's say you're trying to map, I don't know, pine, right, or spruce. So there is considerable variation between the signal that is received by the satellite, which varies with the topography and the soil conditions in different areas. So the mass produced are not they can be improved upon, but I feel that the issue of data leakage can be very easily amended by not depending on shortcuts to collect data, because I feel that a lot of the data that is collected from the perspective of expedience. And okay, we have the sample. It's all here. It's all a spruce forest. So we can use this data, this local data, to map across the whole state. That kind of thinking. I don't think it's really the. As a geographer, I think it's I feel that this is a misrepresentation of the representability of the data, because ideally, when you take samples to predict something, you have to have the full breadth of the distribution of the thing you're trying to sample, you're trying to map, right? And just taking samples that are convenient is not the way to do it. But it's not useless. It's not useless. It's just the first step, and it can be improved upon. I mean, that's.
This is also a very. I mean, this is core question in machine learning research in general. Yeah. Like, what do we generalize towards, and how well do we generalize?
Yeah, I mean, it all depends on the purpose of the map, right? If the map is to if it's for visual purposes, then it doesn't really matter where the samples are coming from, right? But if it's used to make decisions that impact policy, then it has to be as accurate as possible.
I have a question too.
Yeah.
So it's great that you bring up this need for interdisciplinary communication, and so that everybody understands each other and so on. And you yourself earlier, when you introduced yourself, said that you're coming from, let's say, the geography background, and you're applying AI in your projects. So in some sense, you is a person who has like moved on that scale yourself from one domain to the other and mixing. So do you have some like learnings to share? Like, was there something about your AI journey that surprised you, or like that you find is good to know about? It's a bit of a weird question.
Yeah, no, I mean, I see what you're saying. I was actually, when I started this, I was, I guess obsessed is the wrong word, but I was kind of obsessed with accuracy. Like, I was like, yeah, I need to get the best accuracy possible, and that would be the best map possible. And yeah, but I realized that, you know, I started to when I was creating the models, I started to provide or to use data to validate my models that were completely separate from all the other data that I was using. And that was a very uphill battle because I was not getting the accuracies that I wanted. And that really showed me that that this process of producing high quality maps is not as easy as a lot of these Kaggle competitions will have you believe. You know, it's very difficult to actually it's difficult to get a good representative product. So I kind of resigned myself and I said, you know what? I don't want a 98% accuracy. If I get 85%, 84%, and it's generalizable, I'm fine with that. So I've kind of that was my journey. Is that I've stopped pushing for a super high accuracy and more towards something that is more generalizable to what I'm studying.
I have another question.
Yeah.
Thank you for the talk. I really enjoyed it. I wanted to ask you, because you mentioned that the data is there,
Yeah.
and you made your conclusion. But I wonder how much of that data is actually AI ready. Because myself, in projects that I've had in this kind of like multidisciplinary setup, data is there, but not in a format that can go into AI, and also maybe not in a quantity and spread of what you're saying, that you can actually conclude on what you want to conclude.
Right.
So I feel that to add to the efforts that you said, I'd say there's also some data piping thing that needs to happen to be able to make this data AI ready, right?
That's a really good point. That's a really good point because I'm not an AI scientist, so I didn't even think about a data being AI ready, to be honest. Because coming as a geographer and thinking as a geographer, I thought, oh, okay, if the data has a latitude and longitude, I'm happy. If it has a location, I'm happy, and a variable that needs to be mapped. But you're right, you know, a data has to be in a structure that the AI can optimize. And honestly, I don't have the answer to that question because I don't know what is a good format or a good structure for the data to be in, and that's something that I think needs to be explored. Yeah.
Yeah. So it was more of a comment of saying that is also something that I personally feel that is overlooked. That this plays a key.
It's a really good point. Yeah, it's a really good point
to make the whole thing work together. You know?
Yeah, I think it could be something because a lot of this data that I showed, the list of national monitoring schemes, a lot of them fall under the Environmental Protection Agency and the Forest Agency. So it'd be really nice to actually have some sort of I don't know, conference workshop in order to make this information AI ready for this revolution that we want to happen.
Yeah, absolutely. Because, for example, like, I don't know, you mentioned some of efforts that are made for like mapping things, like these kind of things that maybe people do some annotations and stuff.
Yeah.
Maybe you have the feeling that there's annotated data, but maybe everyone annotates it differently.
Yeah.
Or maybe it's not annotated exactly. So then you get into a situation where there's some weak labeling and there's like diversity of labeling.
True.
And that's a whole field of AI research that, so there is that component is important for making this thing work. And I think that's a great idea. Yeah. There was some effort to
bring everything together. Yeah, no, it's true. Like, for example, the data that I'm using for the forest mapping, it's really difficult to work with. I mean, we were talking about this before, right? It's really difficult to work with because it comes in a format that is not conducive to mapping. But, you know, it would not be fair to ask, you know, the forest agency, hey, you guys got to change the way you've been sampling for the last 100 years. You know, so we have to figure out a way to kind of work with that and kind of augment it for it to be usable in large scale mapping.
We have further questions on Zoom.
I have a question about your Tunisia study. You mentioned the migrating birds, and you mentioned that that the results you made in that project were actually useful for policymaking. And so my question is not very well formed in my head, but it's regarding the policy making part, and how do you interact with policymakers, and how do you ensure that your work is really useful for that downstream task of making the policies.
Yeah, I mean, that's really you grab them and make them sit and listen to you. No, no, it's really that's a tough one, because the best that as researchers who are not affiliated with, I mean, the HATE or an agency, the best that we can do is provide clear science that can be followed, right? But in an ideal scenario, we didn't have this for the Tunisia study, unfortunately, because it was difficult to make the connections. But in an ideal scenario, the stakeholders are involved within the research from the beginning. And then when the results come in, you work with the stakeholders in order to provide key points that will form a policy. I mean, that's the way it's supposed to work. We didn't do that for several different reasons, access to policymakers being one of them. But the answer is that, you know, the stakeholders should be involved from the beginning of the process. And because the problem that often happens is that you make good science, you produce fantastic results, and then you give it to the stakeholders, and they're like, I didn't ask for this. You know, I'm not interested in this. So it's really important to kind of begin the process early, so that the stakeholders have a vested interest in seeing this through.
I have a comment on that. I think it's a very important question that's being raised here. I mean, it's something I think about a lot too.
Yeah.
And I agree about most of what you're saying about including the stakeholders. But I guess one potential downside that I come to think of is also that it can also water down the results to some extent. I mean, there is always the risk of stakeholders not really liking what you find. And you hear horror stories about that. Like, I mean, how are you going to communicate? I mean, there's this, to remain sort of stringent to the science versus what is politically okay to do. That's not always so easy.
Yeah, I got you. I understand what you're saying, and that could happen. But I feel I don't know how to answer, honestly. But I think maybe setting up clear guidelines at the beginning might be the way, you know. Sometimes like for these grants for formats and stuff, you have to have these steps about including stakeholders, right? Yeah. So the way I usually pitch it is that the stakeholder will be involved at the beginning of the project, and they'll be informed. This is what we're interested in doing, like how provide your input into this process, and then sometime in the middle, and then sometime at the end. That kind of would limit the influence of stakeholders into the actual science itself, while they will also get the outputs of the results. So there's a way to kind of mitigate that. If there's a problem of them being there continuously, then you can kind of segment their presence or their involvement.
Absolutely. Yeah. Okay, so but I think if there's no further questions within this particular session, we can conclude, and some of us can stay here in the room and Lund and discuss more.
Yes.
So we thank the speaker again for coming today, I think.
Thank you.
And before concluding today, I'd just like to mention that we have a seminar in, I believe, 2 weeks, or 6th of March, where we have Atakan Aral at University of Vienna who will come. So come down as well. Thank you for today. Bye.